thank you for inviting me. I think I was thinking about it, and last time I visited was 10 years ago. So lots of things have changed. And today I'm going to talk about, I was thinking, what should I name the title for this talk? And I really wanted to raise a question. Where are the field robots? And I believe they're in your labs. And, well, how do we get them out of there and into the fields? So I'm going to talk about that. I'm going to talk broadly about my work that includes the work at the university as well as with the startups. I've tried to synergize those things without causing a lot of overlap, which is a balancing act. But I think it's really necessary. Somebody today called me an end-to-end robotics person, and that's very true. I believe very much in creating algorithms and creating ideas in the lab, but I also believe very much in getting those out and into the field. And nice to see Rajan here, who worked with me back in the day at UIUC. So originally I'm from India, and like many people's ancestors in a couple of generations ago, my dad used to have a farm, which was spectacularly loss generating, and and he stopped doing it. Along the way, I've been at many places, Georgia Tech, MIT, Oklahoma State, and I've been involved in entrepreneurial activities all the way through. I was a part of my advisor startup at Georgia Tech called Adaptive Flight, and then these two startups, which very graciously folded later on, and then now EarthSense, which has been going pretty well for a while now. So I'm an aerospace engineer by training, and when I was growing up as a little child, I wanted to go to Mars. And then I started studying aerospace engineering and got more into drones and robotics, and I started realizing that there's a lot of things that you have to do on Earth, right? So what do you do when you go to Mars? You have to terraform the planet. Well, there's a lot of terraforming that we need to do here on Earth. So I started thinking about how do I build a program that is focused on doing that. And so that's kind of what my group does. We work on autonomous robots, particularly field robots. And we are a diverse set of individuals from computer science, mechanical engineering, electrical engineering, ag engineering, and all over the place. And our main goal is to kind of create at the lab the science that drives robotics, and then with our partners, the robots that actually go out there and cause changes. So the way I look at field robotics or robotics overall is kind of this triangle, right? You have perception, planning, and control, right? And at the middle of it is the system. And one of the key things that I really believe in is that all of these things have to work together. And in order for them to work in the field, which is an unstructured, unpredictable, dynamic environment, they have to be in a way that they adapt and they work together. So this is an example of some of the work that I used to do back when I was at Georgia Tech. It's an aircraft that is flying, and then suddenly, in midair, it throws half of its wing off, right? What happens? I mean, this is the reason why we have pilots in airplanes, right? I mean, what happens when such emergencies come up? So how can we create autonomy algorithms that adapt to these changes, that work through these uncertain environments, and bring that AI that's on there to the extreme? So back in the day when I did this, a lot of it was model-based, right? So using predicted models of how the aircraft would behave, planning and doing control based off of that. And you see actually stays in the air and kind of enters this stable limit cycle. This is the Georgia Tech Twin Star aircraft, which has about a 2-meter wingspan, and kind of keeps flying with half the wing off. And with half the wing off, the half of the aileron is off. But the journey for me since then has been, how do you bring this adaptability into robots so that they can work in real world environments and deal with real challenges and do useful things? And then, overall, I'm not the only one. Of course, there's a pretty large community that works on field robots. And when you think of field robots, you kind of think of these types of things, right? Legged robots, bipedal robot, driving robots. I've been a part of several workshops. And I think it's pretty clear that field robots hold the key to a lot of problems facing sustainability, right? So if obviously electric ride share, now that's kind of pretty much on the way here. Climate smart construction, sustainable agriculture, which I'll talk about, and I'll talk a little bit about sustainable solar. But I purposefully picked these pictures because you see there's like these humanoid robots trying to do things, right? So just as silly as it is to have a humanoid drive a car for your autonomous driving, I want to make the point that the robots that actually end up being successful and actually end up being working may not look anything like the robots that most people think of, and really have to be a product or co-design of the task and the software together. So, and this is, a lot of this actually inspired when I was, growing up as an academic or as a graduate student, is inspired by the work by Andrew Ng, and the first aircraft that did the flips, and of course Sebastian, which of whom I heard a lot about at MIT, because the team that competed against Stanford was MIT, which didn't win, right? So, but I mean, a lot of the effort that these early robotics engineers put in was towards co-designing hardware, software, so that we have reliable robots. So here are my main points that I'm going to make through this talk. So where are the field robots? They're stuck in labs. How do we get them out of the labs? Well, we need to think about scaling up. We need to think about continuous learning and adaptation on the fly. We need to think about performance in the open world, not in structured environments, and common sense. So towards that, the journey to date has been discovering a philosophy. And this philosophy, I called this philosophy the Terra philosophy. So the T stands for terrain adaptability or task adaptability, E for energy efficiency, R for robustness, reliability, and affordability. So what I'm going to do now is I'm going to show you 4 or 5 of examples of robots that we have created while we were discovering this philosophy, describe to you the journey and the impacts that these robots are right now causing. So first we'll start with agriculture. So agriculture, as you know, I mean, California is huge in agriculture, right? One of the largest agriculture producing state. The agriculture here is quite different than that in the Midwest. In the Midwest, we do a lot of corn and soybean agriculture. And the key kind of tenet of the agricultural robotics work that I'm doing is that there's this labor bottleneck that's causing unsustainable practices to be used. And the idea is that robotics and AI will help alleviate those labor bottlenecks. So this is an interesting paper by Foley that appeared in Science. And it talks about, like what is the cost of producing food today compared to the amount of food that we're growing. And you might have heard something about how we're going to be 10 billion people by, in the next few years, and that's going to be a big problem. And in all honesty, we need to increase the amount of food that we're growing, but we also need to bring in control the cost of that. And I'm talking about the environmental cost, right? So greenhouse gas emission, biodiversity loss, water pollution, water withdrawals. So this is called sustainable intensification. So how do we do this? So one of the most unsustainable crops that's out there is corn. So there's 200 million acres of it in all of the I states, and it's what we call a large-scale monoculture. So you take large swaths of land, you clear it of everything else, and just plant corn. And because you're moving the prairie away from its natural state of equilibrium, you have to put a lot of chemicals in to make that work, right? So herbicides, fungicides, fertilizers. But the problem is that this system of large-scale monocultures is, not only is it unsustainable, but it's failing. So you might have heard of a pesticide in your waters, right? But there's also a huge challenge with the herbicides that folks are using. So the weeds are becoming herbicide resistant. And this is not like anything mythical. You actually see it now. If you drive down in Champaign a few years ago, we didn't have a lot of weeds visible. But now, like close to the end of the season, you see these weeds popping up out of this soybean crop, and to a level where sometimes it's impossible to harvest, right? So this, according to some people, is a real doomsday kind of situation. The large equipment that we use to enable these large farms. So a normal farmer in the Midwest will have 2,500 acres of land under control. It is not contiguous land. It is parcels of land that are distributed all over the place. And the only way they get anything done is by using these very large machines, right? But these machines cause soil compaction, they cause erosion, they cause nutrient loss. And on the other side of the world, if you look at another very unsustainable crop, which I'll talk a little bit about, which is palm oil, crops like that cause significant deforestation and loss of biodiversity. And even with all of this is just with corn and soybean, the trends are that our yields are not actually matching the demand. So one way to address this challenge is by adding new options for farmers, right? So today farmers can either use manual labor or use large tractors. Manual labor is great for small-scale farming. Large tractors are great for very large-scale monocultures. There's really nothing in between. So one of the ideas that we started thinking about 6-7 years ago was, can we use a number of small robots that can work together and do things that are today not possible due to unavailability of labor, such as phenotyping, mechanical weeding, cover cropping. And I'll talk a little bit about some of these things. And this idea of robots in agriculture is not very new, right? I mean, people have been talking about this for at least 10-15 years, but it's very challenging. And even though there's a number of companies out there that are trying to do it, the problems are really hard because the scales are very large, the field is very messy, and whatever data there is not really representative of what actually happens in the environments. So where are the ag robots? So even though you see a number of these companies coming up and robots coming up, we haven't really seen a large-scale adoption. And if you really kind of peel the onion, and there's a lot of interesting work on this, everything boils down to cost, right? So we cannot use the same ways or same methods that we're using for autonomous driving, in which we're using like a lot of sensors and kind of over-sensing the problem, mapping everything out. We have to find ways in which we can reduce the cost while also making the robots work. So this is something that we came up with, this idea of levels of autonomy for robots, right? So we need to grow up the levels, but as every level, as we go up every level, and about level 3 is when we have what some people call the MVP, the minimum viable product, because you're using a team of robots to basically get the work of a single tractor done. You need to also at the same time bring the cost down. So now I'll give you the first example of how we've been trying to do that. And this robot is called Terra Sentia. And we have made about 80 of these, and I think you were involved in this robot. And these are actually deployed in the field. So corn, right, which is everywhere in the Midwest, turns out it's actually not a natural crop, in the sense that if you go back through the history of agriculture, you won't find a natural ancestor of corn. What you find is this thing called teosinte, which looks nothing like corn. But the Native American people in South America selectively bred teosinte with other crops to create corn. And there's a very interesting article on this in the New York Times. And it turns out that only about 3,000 years ago, the latest varieties of corn, were created. And right now, even under the North Pole, the modern varieties of corn are stored. So in case we get hit by a meteorite, we don't have to go 3,000 years back, right? But of course, that pace of breeding, that cannot keep up with what's happening today. So the seeds the only way you can make a single farmer deal with 2,500 acres is to create seeds that are super adapted to the environment, right? So in India, this is a joke that I used to make. Like in India, if a bug eats a plant, right, the plant dies. But in the Midwest, if a bug tries to eat a properly bred corn plant, the bug will die, right? So that's the idea. But the pace is just not matching up. So in order to feed the world, we really need to accelerate this pace. So to do this, modern crop scientists use a technique called genome-wide association, with other techniques. And what happens there is that you sequence all the genomes, and you measure the environment, and you're looking for the patterns in the genomics that represent specific phenotypes. For example, disease resistant, yield, right? And once you find them, then your job is to then use techniques like CRISPR to then create the crop that accelerates those traits. But we don't have a model. We don't have a simulation of plants. So the only way you can do that is by running very large-scale trials. So what these companies do is they run like hundreds of thousands of acres of trials. This is one example of a 90-acre trial in which, if you look carefully, this is a sorghum trial. Each of these blocks, I don't know if you can see, there are blocks here, is a different variety of the crop, and they're being compared against each other. And the challenge is in measuring all of this, right? So you get quantitative data so that you know which ones are doing better. And today, all of those measurements are manual. And this results in what we call the phenotyping bottleneck, right? So these folks are counting, measuring stem height, stem width. These are really difficult things to measure and take forever time. So you can automate that using gantries or drones, but neither of those see under the canopy, which is where robots come in, but most robots are over the canopy. So in 2017, we introduced this 3D printed robot called TerraSentia, which won the Best Paper Award at the Robotic Science and Systems conference. And the idea was really this small robot that can go under the canopy and use machine learning techniques to basically do simple phenotype. In this case, it was counting. And the genesis of that robot was that before we started working on that robot, these were the kinds of robots that were out there. So this is a robot that was made before I came to UIUC. It's a tracked robot, and people are using all these like kind of best practices. So, you know, people thought, well, you have to make a tracked robot because it's the field. But you see here, this robot kind of drags that plant down. You have to put a mast on it because you want to see down, and you have to put the most expensive sensor that you can find on it. But the reality was that while that was an expensive and interesting robot, it actually didn't do the job that it was supposed to do. So that's where kind of like, as we learned from the world of drones, that miniaturizing a helicopter, right, was not the solution. We had to come up with a drone which, is not something that a human would fly in, right? Because it's impossible to fly until you put an IMU on it. So a student of mine then came up with this idea, like, why are we trying to do all of this? Why don't we just take our drone and kind of make it run on the ground? But obviously you cannot fly it through there because the endurance just wouldn't be there. So we came up with this 3D printed robot, and I think it was just a very basic idea of just taking those motors and flipping them down, and each of them having their own motor, and there was no other moving part other than that, and then trying to see, and then putting a camera on there to see how well that works. We made, who knows Steve Blank? Anyone know Steve Blank? Lean Startup, right? Stanford person, right, who created this whole philosophy of Lean Startup. So we had a I-Core project, NSF I-Core project, and we went and we engaged with customers. And we said we made 30 of these 3D printed robots and we gave them to customers. And we said, okay, we'll go use them in the field. We'll see how well that works. And literally some of them melted in the field, because field environments are very difficult. So at around the same time, this company EarthSense that I co-founded took over that project and became a technology partner in the ARPA-E TerraMap project, and created this robot called TerraSentia, in which Rajan was a part of creating the drivetrain, right? So this was a very different field robot compared to the ones that were out there. It was made with hub motors, so each wheel was itself a motor. There was no connections other than that, so directly you connected your arm to the wheels. These motors were, because they're hub motors, they're contactless, brushless hub motors. They can go through water, they can go through snow, they can go through all kinds of different terrain, and the robot was extremely tough, as is shown in this example. So this was, I think, the 2020 or 2021 version of that robot. We iterated across 3 years, and every year we try to improve the robot, and finally bringing it to this level of maturity. So this is one of our engineers just loading up the robot with some weight. And the robot itself weighs no more than 20 kilos. Right? Then he's sitting on it, and then the robot pulls this 400 series tractor. Right? So I think it was very interesting, getting into the design space there and figuring out how we can use electric propulsion to kind of make sure that we pack a lot of power in very tiny machines. So that was, that's great. That was one part. The other part was trying to get these robots to be autonomous. So the standard way of doing that is with Global Positioning System, GPS, right? And it works great on John Deere TrueTrack and Trimble's GPS systems because they have clear view of the sky. But once you start going under the canopy, and we did a lot of work on this, one of the a part of a number of papers that one of my students wrote, who's now at University of Oklahoma as a professor, was figuring out these traction coefficients in real time and using them to improve the control, and using techniques like model predictive control and receding horizon estimators to kind of to really improve the accuracy of GPS. But the problem is, once you go under the planned canopy, whereas with a real-time kinematic RTK GPS, you're supposed to get under 2 centimeters accuracy, the accuracy drops to 40 centimeters, right? Because the signals bounce off of the plants. So we started in about 2019 working on, well, how do we solve this problem using exteroception, right? And we pose this problem as a row following behavior problem. So using a single sensor, can we figure out the distance to the row and the angle to the row? And this is, in a setting like here, this is a LiDAR point cloud. So the LiDAR is here. Again, we're trying to reduce the cost of the LiDAR. So it's a $1,000 LiDAR. And these are all the plants here. So you see it's a completely messy point cloud. Whereas if you try to drive here, you'll get a very nice line on which you can fit a line. So fitting the lines on that LiDAR point cloud was one of the first key challenges that we had to solve. That's explained in this paper here, and we came up with a method that was basically a accelerated form of line fitting in the presence of outliers, and then we kind of created that and put it onto the robots. So this is an example of me giving that robot a hard time as it's driving down the field with this algorithm on it. And this is kind of where we started forming this philosophy that, okay, you can create a paper, you can write a paper, you can create an algorithm, but the real test is to go out there and can you kick the robot, right? So that's what I tell my students. Your robot has to be kickable before you can graduate. So here you can see it's a very tiny sensor right here, and the plants are all around it. And with this EarthSense, this was just a part of it. Of course, the company did a whole other set of development that is proprietary, but they created like this first product that started to make sense in the space of agriculture. So this is a high throughput phenotyping product. It's a robot that goes through the rows of corn. It's detecting and measuring individual ears of corn, and then reporting back this data on essentially a plant-by-plant basis to the breeders, right? In a front-end system that looks like this. This is a National Science Foundation project called CROPS, and this is a field map. So each of those plots represent the grid that I showed you before, and that's the height, plant height, ear height, measuring at the same time 4 traits and across different time stamps, so you can get like a full high throughput view of that. And we have a paper, hopefully that'll come out by the end of this, maybe early spring, that shows how well that works across multiple years on data with a very large company. So taking that same idea, this is just measuring, and it is limited to crop breeding. We wanted to bring that idea to farmers. So in the Midwest, the agriculture is very seasonal, right? So we have right now, when I left Chicago, the temperature was 18 degrees Fahrenheit, right? So it's freezing, and there's basically nothing that lives. So from basically November all the way into March, we leave these 200 million acres entirely bare, right? And then before planting happens in around June or late May, weeds come up and the soil degenerates and all kinds of things happen, right? So, but there's, but there's a way, and this soil could be doing useful things, right? So you can grow cover crops on it, and cover crops can do a number of things. They can sequester carbon, they can fix nitrogen, they can hold nitrogen that's excess, and they can break up compaction, right? So different types of cover crops can do different things. Now there's also cover crops that can be used for harvesting, like they can create biomass that can be used to create sustainable aviation fuel, for example. But most farmers are not able to do it. So this is around Thanksgiving. If you try to land in Champaign, you see what I call the corn and soybean desert, right? It's just like acres and acres of bare land. And the problem is that they harvest somewhere around September. And if they try to get cover crops planted after that, the sunlight days are really not there, right? So by November, it starts to get cold, and they can't really do this. So we had this idea, well, what if we created a robot that could go through the canopy and broadcast seeds? So using the same kind of technology that we were using, but broadcast seeds so we can have cover crop planting done as early as August in standing corn. So, and we could, and with a lot of economic analysis, we can show that it can be done at a much lower cost. But the problem is you need to bring the cost of the robot further down, right? And you need to make it more reliable. So LiDAR-based autonomy is just not enough. So we had to change the sensors and think about using cameras. So these cameras cost $30, whereas the LiDARs cost like about $1,000. But that's a very challenging problem, right? Because fields, are really messy when you try to do it with monocular vision. So we worked together to create a method called crop follow, and Arun, who is about to graduate, worked on this. And here the idea was, we thought about many different ways of doing it. The one way you could do it is with using techniques like reinforcement learning, right? So where you basically learn everything from scratch and try to see how that whole setup works. But the problem with that is it's really difficult to debug. And then in this high mix, low volume manufacturing setup, these robots are individually very different. And because of that, it becomes very, very hard to find where the issues are. And of course, we had a fully working system also. So what we did is that we just swapped this distance and angle estimation with vision. And we said that, can we find distance to the row and angle to the row with a single vision? So basically, you have a single vision, single camera, a monocular camera, an image from the camera goes in, it goes through a neural network, and it predicts the distance to the row and the angle with respect to the row. And this was, so we started doing this in about 2019. And, back then we did it with labeling, like heavily supervised learning. So we labeled about 26,000 images, using all kinds of techniques where you can correct the image when you don't see the horizon. We use the plant as the way of seeing the horizon, measure the roll and pitch, and then get basically a good estimate of where the crossing points are. And then we used that to train this model, and then we started testing it in the real world, and it worked really well. So these are some examples of this vision-based autonomy. You can see the terrain is really challenging, and the robot is able to kind of tolerate early season, late season, a small curve, and through significant occlusions. And so we deployed this, and this is now Arun, and you can tell that he's ready to graduate because he's starting to kick his robot now. He's a lot more gentler, although also there's a number of other things that were also changed. As you can see, the robot's also controlling its speed now in order to. So there's like a little planning module on there which is trying to control the speed as well as the angle of the robot to make sure that it's going on its path. And I think this is like, can you see the plants? This is early season soybean. So obviously the LiDAR isn't working because the plants are not as tall as the LiDAR. And then after a while, the robot will enter in early season corn. The same, just going straight. This is at the Farm of the Future at Illinois. So anyway, let me see. Just push it forward a bit. Yeah, so just seamlessly transitions into early season corn and continues to go. So this was great, and then we took it, and this and several other methods were then we tried to do a large scale experiment with it, and then we started finding out that even though everything worked great in the paper, and we were able to get again very large sets of validations, and it was an RSS paper, 25 kilometers I think. The fact is that when you started to deploy it beyond that, we started to see a lot of issues. So one of the issues was that the environment changes. There's really no uncertainty prediction. So because the environment changes, we basically end up with a domain shift. And because the cameras on these robots are differently calibrated and installed with slight defects, right? What works on one robot doesn't work on the other, right? There's like little biases that creep up. So in last year, this year, 2024, we published another paper called Crop Follow Plus Plus, in which now instead of doing the full angle to row, we're basically creating a confidence estimate of where the horizons are. So 3 points, right? The end of the horizon point, the 2 points here at the side, and then combine that with AI to detect failures and recover from failures when they happen. So this is an example of that happening. So there were two sets of papers. So one was the 2024 RSS, and the other was the ICRA 2023 paper, in which kind of put that together. And that kind of is working really well now, and that's what creates this this kind of an idea. So you have a robot which can go through standing rows of corn and distribute seeds of corn together. And when you have, so there's new types of distribution methods that are now coming out. Each robot can cover 9 rows. So 4 rows on one side and 4 rows on the other side and the row that it's in. So each robot can cover 9 rows at a time. So if you have 10 robots, you can cover 90 rows at the same time, right? So driving at about 1 meter per second, these robots can get the whole field planted in less than 5 hours, right? Which then becomes, and a whole field the size of 100 acres, right? So that starts to now then compete against thing. And by the time you harvest, there's already a standing cover crop there. So this is a very iconic picture, right? I mean, the harvester has just gone through and the cover crops already has emerged. So now we have, at the Farm of the Future, we did an experiment comparing robots versus tractors. And you can see by spring, the cover crop that's planted with robots is really robust and healthy, and we get a really nice benefits from these types of crops. We have a large grant now to try and scale this up with a target of many thousands of acres next year, and trying to really bring this technology to fruition. Now I'll talk about another example of the Terra philosophy with a robot called TerraMax. And this is now all the way on the other side of the world in Malaysia, in palm oil plantations. So palm oil is one of the most consumed oil. So apparently 50% of supermarket products have palm oil, right? I mean, less so nowadays because of all kinds of issues in the US. But if you go to Asia, I think a lot of, even Cadbury's chocolate has palm oil, and in my opinion, it tastes better. But so the palm oil is tasteless, right? It's really, it's a vegetable oil. It can be used pretty well. But the issue with it is that it's a huge contributor to deforestation, and it has very serious labor challenges, right? Basically, significant issues with contract labor. I mean, and a key problem with palm oil, especially in places like Malaysia, is that labor is just very difficult to get and very difficult to retain, right? So, for example, 20% of palm oil growers were able to hire only 20% of the, palm oil growers are only able to hire 20% of the labor that they needed in 2022, and the losses are just in many billions of dollars. And people often wonder, well, why are we so worried about this anyway? Like, what's the big deal about palm oil, right? It's all the way in Asia. But so these are two very revealing charts. So here, this is the amount of palm oil yield that you can get per hectare. And you can see that it's just, it's crazy compared to all these other oils that you can get. Soybean oil is here, right? It's 3 times that of soybean oil. And in the amount of land that you need to meet the global demand, right? So basically 8.6% of the land under palm cultivation meets 36% of production, right? Whereas with soybean, we have almost 40% of the land under production, and we are only meeting 25%. And if you think of sustainable aviation fuel, palm oil is really the only way to get there, right? Because we can meet global fuel demand with about 84 million hectares of palm oil, which is really, off the chart compared to all the other ways. So there really isn't any option. The only real option left is to try and make palm oil production more sustainable and more, fair in terms of labor. Now, many countries are trying to reduce the area under palm oil cultivation. Malaysia is in the forefront. They've managed to stabilize it and bring it down just a little bit. They've guaranteed that no more than 50% of the country will be used for agriculture. And the idea here is, well, can we use robots and AI to kind of make production better? For example, using things like precision fertilization, precision spraying, and over time harvesting, bunch transport. So for this purpose, we created a robot called TerraMax. Now, TerraMax is a completely different robot. It's a 500 kilo robot that's much larger than our other robots. It still uses the same types of techniques, so individual wheel motors, no variable transmission shaft, so there's no transmission. So the two wheels can operate completely independent of each other, right? They each have their own suspension. It can tackle really challenging terrain, and the middle part is open for putting different types of payloads, right? So in this case, it's a fertilizer bin, and then you'll see that it does some spreading right here, fertilizer spreading. And it's a fully electric battery-operated robot that we're learning a lot about optimizing the motors to do this. And just as a comparison, that's Terra Sentia, and that's Terramax, right? It's a totally different robot. So in September, I was in Malaysia, and we managed to do 102 hectares in 7 days. It was a challenge that was set forth by the industry to see how scalable or will this technology work. And it was quite exciting. And here's just some snippets. And of course, like I think from a research perspective, these robots use some of the techniques that I talked about, but of course, way more than that, right? So they ended up using a technique in which this type of row following is combined with basically semantic segmentation, right? And large-scale semantic segmentation combined with the row following creates like a pretty good understanding for the robot where it is. That's combined with the GPS data that it's getting, and then it's you saw in that video that it's detecting individual trees, distance to the trees, and then executing maneuvers. And it's quite challenging because there's a ditch right here, there's a ditch on that other side, there's a ditch here. It's quite challenging, this environment. But it seems it's been doing pretty well. We also have remote monitoring systems in place so that we can kind of keep an eye on what's going on and then get this robot to drive autonomously. And everything here I'm showing you is autonomous, right? So that is the benefit of not having a transmission. So basically wheels are totally imbalanced, but the robot is able to go through some really tough terrain. So that's my engineer. She's just delighted that it tackled that. This is basically, and it rains every day in Malaysia, so you can't avoid muddy puddles. But of course, even with that, the robots fall down. And one of the big lessons that we've learned now is that you really cannot try to make the whole system fully autonomous. You really have to think about increasing throughput. So here the robot fell into the ditch. It was pulled out by the tractor and immediately resumed work, right? I mean, it was not a showstopper by any means. But essentially, I think one of the big philosophies that's coming out of it, and this is after completing the 100 hectares, is that you really have to find ways in which humans and robots work together, as opposed to just imagining that robots will completely replace humans, because we're just not there yet. Because let's say you put the most expensive sensor that you can find, right? You still need somebody to clean it eventually, unless you put a cleaning system. Then if you put a cleaning system, then the cleaning system breaks. So I think we have to start thinking about robotics as an assistive technology. So the other thing I'll talk about now is some of our work in kind of broader field robotics and just algorithms for driving robots, and this method called way-fast. So you see here this tractor driver just using their eyes is basically pulling this very, very, very heavy truck on this completely muddy terrain, right? So if you try to do that with just kind of using GPS or something, it's just not going to work. You have to have experience built in and learning in real-time adaptation to deal with that. So we've been thinking about how to encode that in software. And one way of doing that is what we call way-fast, which is waypoint-free adaptive navigation, right? So basically, you give only a single waypoint where the robot has to go, and the robot gets data from its sensors, like essentially stereo cameras, and creates a traversability and traction map just based off of that data, just like a human would do. So this is an example of, so this is a fully self-supervised method that basically takes in an image and creates a traction map, which then becomes a cost function for a controller that then generates a path for the robot. So the way we do this is we start with like a standard robot model, and that's really cool because we can easily swap this model whenever the robot changes. So the system is pretty scalable. And we add to it these traction parameters that we talked about before. We estimate these traction parameters in real time, and then that becomes the labels for the images that the robot creates. So in the training time, the robot's driving around, it's estimating the traction as driving around, and that data is correlated back with images. Those images are then used in exploration stage for training. So here, for example, you can see as you're going around, the robot is driven and it hits different things, and the traction that it experiences is encoded by itself. So then you take an RGBD image and you create a traversability map using that data. That traversability map becomes a cost function for the model predictive controller, and that creates the actions that drives the robot. And so you see some examples here. So white is traversable or with good traction, and dark is not with good traction. So you can see here the robot clearly can say that snow is not as traversable as clear terrain. Similarly with trees, and not only that, it also creates like a boundary around it because it knows once it hits it, it'll get stuck. And remember, none of this is with labeling, whereas the first bit I was showing you was all with labeling. This is all happening by, the robot's doing this all by itself. And so this is in real time an example of how the traversability map looks like as the robot is driving around. And you can see these are like the areas that are not traversable. And then these nice behaviors emerge. So the robot knows to avoid the tree, and that's, I guess, fairly geometric. But the other interesting thing is that obstacles that are not geometric, for example, this ditch, it knows to avoid that based on the visual data. And then in this case, it knows that it can go through grass because grass is traversable. It doesn't really lose any traction there. But when it comes to the tree, it has to avoid it. But on the other hand, if it was using a LiDAR, grass would look exactly as untraversable as a tree, right? So more recently, we have then tried to take a batch of data in real time also, like a sequence of images, feed it into the network, and create like a 3D map around the traversability map around the robot. So this is what the robot creates like a bird's eye view traversability map as the robot is driving. And these are all the different trajectories that it's thinking about and picking one of them. And you can get some really cool behaviors. Again, it knows it can go through grass because it doesn't lose traction, but it will avoid trees. And then in this example here, this is the Campanile on the South Quad at UIUC. And it basically sees this pillar. And even though it's not in view, it remains in the map, right, for a while, so that the robot can plan. If it has to back up or something, it knows that it exists, and the plan can be done with respect to that. Let's see. We have only a few minutes left. Okay, and then this is the last bit that I'm going to talk about, the philosophy again of hybrid soft manipulation. So today's robots, right, tractors are really good for low dexterous tasks, but they scale up very well. Humans are really good for small scale tasks. They have a large level of dexterity. And robots that we have today are really not good at either of them. So the goal is to try and create robots that can have high level of dexterity as well as scale up well. So towards that, we've been thinking about how to create different types of robots. So I've been working with a friend of mine, Girish Krishnan, who's a professor at UIUC, as well as Mattia Gazzola and Sarah, who is the expert in polycultures, to create new robotic concepts that would work well in a cluttered setting like a polyculture, in which different varieties of plants are planted together so that they can grow together. And so these arms are essentially, they're called frees. They're basically tubes wrapped around with a filament, and they're wrapped, each of them is wrapped in a different way so that when you pressure it, they bend in a particular way. So by controlling the pressure and the wrappings on the different types of tubes, you can create muscle-like structure and bend these things any which way. In 2020, we had a paper at RSS in which we basically combined the arm, the free arm, with a rigid arm to create like a hybrid manipulator. So the idea was that if the berry, or if the target is not within the reach of the rigid arm, then you move the soft arm out or whatever, and bend it in any which way to get it. And the reason to do that is because the rigid arm is really much faster, right? It's very fast. You can move it really fast, but it doesn't have the dexterity. But the soft arm can reach all these different places, but it doesn't have the speed. So can we combine it together? And I'll just show you some results that aren't yet published, but hopefully soon will be, about just trying to get these hybrid manipulators to work in an intelligent way. So you must have seen a lot of this type of work with rigid manipulators, right? Where robots are detecting objects, creating 3D representations, and picking things up. And there's a lot of very interesting thing in which these are also connected with large language models. We want to do the similar thing, but with these hybrid arms. So the way the pipeline works is you get an RGB image. We create a 3D reconstruction using a network called master. Then, of course, there's a standard image segmentation network that can help find objects. This then creates an occupancy grid, a mental map of where everything is. Then you make a path, and in planning the path, you use a model of the soft arm, and then this creates then goes through another network and creates the actuation. And the idea is that by creating paths that are separate for the rigid and the soft part, you can make sure that the rigid arm is not bumping into anything or touching anything, but the soft arm, you don't have that constraint anymore. You can touch and you can coil around things. So again, like, this work is still going on, but here are some examples of what we're seeing. So there's one single camera at the end of the manipulator in the soft arm, and we're using that to create these 3D reconstructions. And then I guess I'll just show you the video. So in this case, the robot has to reach this. The end effector has to reach this bottle, and the data that's coming is from this eye in hand camera that's here, and you see that it's able to get to it. In this case, it has to reach this orange, and you see that it'll basically go around that thing, but it'll move the plant knowing that the soft part can touch and interact with the plant, but the hard part kind of stays away from this. And then in this case, it's going to reach the hole, again using the same kind of a technique. I guess the next time we show this video, the robot will have gone through the hole to do manipulation on the other side. Okay, so I'll kind of end this here with kind of a view to the future of one other application that we're trying to apply the Terra philosophy to, and that's solar plant operations and maintenance. So, California is actually the largest solar state also, right? California has one of the largest solar farms, which is in Mojave, right, which is not that far from here. And these are very large farms, right? There's like 10,000 acres, 50 acres, 10,000 acres under cover. And they have a payoff period of about 10 to 12 years, right? But the problem is that due to issues in manufacturing, due to grass that grows, due to micro cracks and things, solar panels and the surrounding stuff can actually catch on fire. And that creates a huge hazard. And there's a number of other maintenance operations that need to happen. So one of the things that we're thinking about now is how can we use robots to go out there and use the same kind of technology that we have for under canopy navigation to get near the panels and do things like repair and maintenance. So, and this is just like a kind of a quick demo of this thing. We're calling this thing TerraWise. Again, it's like a very simple robot. This is a prototype that goes through this panel. When it was driving, it was 50 degrees centigrade outside, right? So pretty hot. And then has cameras on it that can help it find things like combiner boxes, MC4 connectors, things like that. So it's pretty interesting. It's early days for this technology, but interesting to see how it evolves as these robots become more practical. Okay, so I want to kind of end it here. And one of the things that's really fun about the work that we do is brings together a whole different variety of people across the campus at UIUC, right? From the engineering quad to the agriculture quad to socioeconomic people and extension, which is how the university engages with farmers. And then I wanted to end with this fun graphic here. MIT Technology Review had this article just a few weeks ago, and robots are coming, right? And that used to be actually the title of my earlier talk. That's why I changed it to Where Are the Robots? So, but and robots are coming and they'll do all these amazing things. But the reality is that robots are AI embodied, right? And if you don't think of co-design of the hardware along with the software, it's very difficult to get to a point where the robot will be task effective. And then people often complain that, what I really wanted is robots that would do my laundry, but what I have is a large language model that will write me poetry, right? So both things are useful. Just some papers that are here, but it's been a lot of fun being in Stanford. I saw and learned a lot of cool things, visiting a number of different labs. So I'd love to continue to chat more and find ways to engage. Yeah. Yeah. Okay. Whoever.
Go ahead. You start.
Yeah, I guess a comment and a question. So in my past life, I did a lot of large-scale phenotyping for specialty crops, melons and berries. And I think there's definitely a need within agricultural robotics to explore non-traditional sensing modalities. LiDAR and camera, I think, are really effective. But I think when you start looking at crops like melons, there's a lot of inclusion in the field where those sensors are no longer valid. We did some work with backscatter X-ray and ground penetrating radar for root crops. And I think there's a large opportunity in agriculture to kind of explore those sensing modalities and make the models more robust and make those algorithms more applicable. And then I guess the question, when you look at crops and how they grow, I think one particular challenge in this space is your perception kind of workspace is changing. The features you're looking for are changing over the year. You might go through a field with seedlings and you can use one set of camera intrinsics to capture all those details. But as the crops grow, the need for different camera intrinsics arise. So how do you think about continuous calibration, or how do you change those sensors to accommodate when you're looking at features on the corn that are 3 feet off the ground versus when you're looking at seedlings and stalks?
Yeah. So at least with corn, I mean, you're right. There is a need to go beyond traditional sensing modalities. We've looked into hyperspectral and multispectral and all of those things. I think from a level of practicality and cost, they're still not there, and we're not able to get useful data from them. The phenotypes that we were measuring were fairly geometric, so it was good enough to do with stereo. Again, I think it boils down to the philosophy of where you do what's practical and you do what scales, because otherwise it gets stuck in the lab, right? So I think in terms of recalibration and stuff, we did. I think with the models and the cameras that we have and the techniques that have been used, they're pretty good. I think we didn't have to recalibrate a lot. There was some retraining that is needed as you change phenotypes, but overall, at least when you have normal cameras that are well calibrated out of the box, and then when you put it on the robot, you calibrate them before you give it to the customer, we had a pretty good performance. Yeah.
I really like the traversability work, and I was curious how much of the way you use that now is based only on your understanding of the environment versus the capabilities of the robot. So if you have a robot that has different types of physical capabilities, I imagine you'd have a different traversability algorithm, and how easy might it be to
Yeah, actually, so I had those slides, but I hid them. We just had a paper published, FedEC. So it was fed wayfast. So federated wayfast. And essentially, you have these different robots, and they basically form a space in the traversability latent space, and then you can combine data from these different robots and different capabilities, different terrains, and create a federated model of traversability. And you can do that without having to move all of the data because there's not a lot of internet connectivity in the fields. Just using federated update techniques, but that's one of the things that we have been working on. Yeah.
I had a question. So some of the newer algorithms look quite computationally heavy. So I was wondering lately, what's the latest and greatest for?
Actually, yeah. So all of the stuff that has been on the robots is designed in a way that it works on the AI, on the computers that are on the robot. And typically that's not, I mean, on the bigger robot we have Orin running, but on the smaller robots it's mostly something like a Jetson. The vision, the key point detection thing returns 20 frames a second on board the robot. So it's been leanified to do that, right? Because you cannot assume access to a large computer or even way fast is pretty fast once it's trained and installed on the robot. Cool.
As you continue to move forward with these robotic systems that are kind of smaller in scale and they're moving through larger terrains with more complex executions, the power draw from the motors and for the entire systems, what do you think is kind of going to be the solution, or is there even a problem with the amount of power that is on board these systems to be able to traverse, and like the operation time, is it still viable?
Yeah, so battery life is has been a very big area of design improvements for us. So we're to a point where we've gotten into the motor design now. So the way it works, so brushless DC motors are brushless DC hub motors can be effective at like a higher RPM range, right? So at a higher RPM, they're very efficient, but you have to run them at low RPM for this thing. So the new types of motors that we are developing now are geared hub motors. So that's I think the best way to extend the duration. So endurance on the Terra Max is about 6 to 7 hours already, and I think we can get it up to about 8 to 9 hours. Endurance on the Terra Sentia is around 2 to 3 hours, and I think we can increase that also with the geared hub motors. The other thing that can be done, which we're doing now on the bigger robots, is a series hybrid powertrain. So you have like a little engine that's using biodiesel, for example, that's running at a constant RPM, right, to just charge the batteries whenever needed, so that if you're stuck somewhere where there isn't a plug nearby, you can run the engine to charge the batteries. But I think, go ahead.
Has there been more, was that something that came from demand from the farmers, or was that something that kind of came from just wanting to extend the battery?
I think it's an intersection of what the farmer wants and what the technology is capable of doing. If you can find an intersection of that, that's when you have a usable solution for the farmer. Right? So farmers obviously don't, like for example in palm or even in corn or wherever, there is no power outlets in the middle of the field. So you have to be able to have enough endurance to basically last the whole mission.
Are there any from the online? No, not really.
Okay, yeah, I think we actually managed to do this on time. That's surprising. Thanks, everyone.